Previously, we said that if we put the major axis of an ellipse on the x-axis, the center of the ellipse at the origin, then we can write the equation of this ellipse with x squared over a squared plus y squared over b squared equals 1, where the b squared is actually a squared minus c squared. There's a different way of doing that, though, and that's what I want to talk about today. Instead of putting the center at the origin, I'm going to put the right-hand focus at the origin instead. Even though I've moved the ellipse, in the original version, the smallest x-coordinate was negative a, the largest was positive a, the length of the major axis is 2 times a, so this distance is still going to be 2 times a. Likewise, this distance is still going to be 2 times b, and this distance is still going to be 2 times c. However, since one of the two foci is now at the origin, the x-coordinate of this focus is negative 2 times c. In the previous description, if you look at a point on the ellipse and add the distance from that point to one focus, plus the distance from that point to the other focus, you have to get 2 times a. That still must be true, except now one of these two distances is just going to be the r of polar coordinates. We still have to figure out distance d1. Now that's easy to do, though, if we use the distance formula. Notice that this is especially nice as opposed to how we did this before, where there were 2 square roots that we had to deal with. In this case, there's only 1. So we'll isolate the 1 square root that shows up in this formula. Then we'll square both sides to get rid of the radical sign. Multiplying things out, I get this formula, and if you'll notice, x squared plus y squared is r squared, so over on this side of the equation there's actually a term, r squared. There is an r squared on this side of the equation. If I subtract r squared from both sides, I can get rid of that as well. In what's left, there's a factor of 4 on every term, so I can get rid of that. In what remains, one term has an x in it, which in polar is r times cosine theta. Another term has a r in it, the a times r term, over on the right. The other two terms, the a squared and the c squared, are constants. So I'm going to group things together that are similar in nature. Since x is r cosine theta, I'll go ahead and write the x times c term using that. I added the a times r term to both sides, and I subtracted c squared from both sides. Factoring the r out, and then also factoring the a out, results in the equation at the bottom of this page. Notice two things. Firstly, a squared minus c squared is b squared. If it was convenient for me to represent things that way, I could do that. Also, c divided by a is the eccentricity of the ellipse. If I do the indicated arithmetic, the r is a constant, b squared divided by a in the numerator, divided by 1 plus the eccentricity times the cosine of the angle theta in polar coordinates. This general appearance is how we will represent an ellipse in polar coordinates. At times, it may be more useful to express this in terms of the biggest and smallest distance, so we can look at that as well. Thinking of this formula as just being r equals a constant divided by 1 plus the eccentricity times cosine theta, if I want to make the r as small as I can make it, the so-called perihelion distance, then I would want to make 1 plus eccentricity times cosine theta as large as I could make it. On the other hand, if I wanted to make r as big as possible, I'd want to make the denominator as small as possible. 1 and the eccentricity are constants. I would want to make the cosine of theta equal to -1 if I want to maximize the r variable. Rearranging these in a very simple way, I can express the constant f in the numerator in terms of either the eccentricity and the perihelion distance, or the eccentricity and the aphelion distance, the greatest distance from the origin. In this way, I can express the formula for my ellipse in terms of the angle variable theta, the eccentricity, and either the smallest or biggest distance from the origin on the elliptical path. Returning to the two formulas that I obtained for this variable f, if I take the fraction of these two quantities, I must get 1. If I take the fraction of these two quantities, I must also get 1. If I measure r min and r max, this will let me figure out what the eccentricity is. Doing a little bit of algebra, I found out that the eccentricity is the biggest r value minus the smallest r value, divided by the biggest r plus the smallest r. So if I were to draw the orbit on a piece of graph paper, you could get a ruler out, measure how far away you get from the origin, how close you get to the origin, write this fraction down, and experimentally measure the eccentricity. This formula has 3 quantities in it: the eccentricity, r min, and r max. If you know 2 of those quantities, you can do algebra to figure the third one out. The reason that I'm interested in this second way of thinking about the equation of an ellipse is one of Kepler's laws says that the orbit of a planet about the sun is an ellipse with one of the 2 foci located at the center of the sun. So if I imagine setting up a coordinate system with the sun at the origin, these kind of equations will describe the path of a planet. We'll see more of this in number 3, the ellipse. I hope everyone has a good day. I'll talk to you again soon.